Today we're going to find out a bit more about electrons, what they like to get up to in their spare time, and more importantly, where do they live? But before that, if you have not already done so, pause the video so you can download the free PDF that goes with this lecture, and yes, it is a lecture. So once you've done that, you can come back here. Okay, so is everybody ready? All right, I will now begin. So, as always, these points match up to the syllabus, and today we are looking at emission spectra, hydrogen emission spectra, number of electrons in each main energy level. So, up first, emission spectra. So, an emission spectra is produced by atoms emitting, so that just means giving out, photons when electrons return to a lower energy level. Okay. So to understand what an emission spectra is, we need to know a little bit more about light. So light is both a wave and a particle. So this is kind of light behaving as a wave. This is kind of what you're familiar with. But light can also be a particle. So it can be tiny little particles moving along. We can have, different particles moving along. So light is both a wave and a particle. So in the world that we enjoy light, light is a wave. And when things get very, very small, light becomes a particle. So tiny little packets of energy. So we know that light is energy. So it becomes tiny little packets of energy. And a particle of light is called a photon. So each photon has a fixed amount of energy. So same with the wavelength. So here, these are like a longer wavelength. So a longer wavelength has a lower energy. So these photons will have a lower energy. Then as you get a shorter wavelength, then it is a higher energy. So these photons over here would have a higher energy. But when you have all of the photons together, what you have is a continuous spectra. So this is what we've got here. So this is the continuous spectra. So this is all of the photons together. But yeah, like if we had, but yeah, these photons over here, if we could just pick out at that specific wavelength, they're all going to have the same energy. Pick out here, yeah, these photons here would have a fixed amount of energy. Alright, so to help us visualize this, we could imagine that a photon is a grain of sand. Here we go, our grains of sand. When you have lots and lots of sand, you have a beach. So this is the model for the continuous spectra. So when you've got everything together, you've got a continuous spectra. And when you have lots and lots of sand, then you have a beach. So there are no gaps in between. But unlike a beach, you can split up a continuous spectra into sections based on energy. Well, we're going to give it a go with the beach. So we could say that this part of the beach down here, so this could be higher energy. Then as we move further away, we continuously move to a lower energy. So with the magnetic spectrum, we can keep breaking up these sections until we are left with photons that only have one type of energy. So this is all of the photons with all of the energy, but we can break it up until we've just got individual parts, and then each part would have only one type of energy. So if we've just got one line, this has only got one type of energy. So you could do sort of the same with the beach. So you could, so with our beach model, you could kind of do the same. You could sort it so that you have grains of sand that were all the same. That doesn't quite work as well. So back to the photons. So it just so happens that photons, the energy that a photon has, is the same energy that is needed to make an electron move to a higher energy level. So these photons can interact with electrons. So we've got a photon coming in. So a photon can come in, so the electron was here, and then it's causing it to jump up to a higher energy level. So the electron jumps from the lower energy to the higher energy. And the key thing is that it never has any energy in between. So it's never in the middle. It's either down here or it's up here. And the gap, that gap is an energy, and that's the same energy that the photon has. Then after a bit of time, the electron falls back down, so from the higher energy to a lower energy, and then the photon is emitted. So yeah, with the electrons are either at a lower energy or a higher energy, or going from a higher energy to a lower energy. They're never in between. So here we've got a little firefly. So I don't know if you've ever seen fireflies. So fireflies kind of glow and they kind of appear, then disappear, but in a different location. So this is the same with the electrons. They start in one place and then they appear somewhere else. They're never in between. All right, so linking this back to emission spectra. So continuous spectra, hopefully we understand. So the continuous spectra is all of the photons all together. So that gives you all of the energies. What we've got here now is, so this is the emission or the line spectra, and this is what we're getting from our diagram over here. So when the photon is leaving, this has a very fixed energy, and then that matches up to a line. A line, a line, a line. So this is our emission spectrum. It's the photons that are leaving, they are being emitted out of an atom. And then the absorption spectra is just kind of the reverse, or like the invert of the line/emission spectra. So this is all of the light that wasn't absorbed by the atom, and then this is just the very small bits of light that were absorbed and then are being emitted. So yeah, a bit of a tricky thing to get your head around, but once it clicks, it does make sense. So we're going to put this into practice now. Right, so now onto the hydrogen emission spectra. So hydrogen's emission spectra provides evidence for the existence of discrete, which means fixed, main energy levels, which is another word for shells, where the electrons can be found. So these energy levels converge, so they get closer together at higher energies. So using these observations, we are about to look at and understanding what an emission spectra is, it is possible to build up an idea of what the structure of the electron shells are. So hydrogen is used for this, as it is the simplest atom, as it has only one electron. And when looking at hydrogen's emission spectra, we will be able to see a bit easier. It's a bit easier to see what is going on. But before we do, let's see how we are getting our spectra. So this experiment I'm sure you have done before. So white light comes in, it's getting split, and you are getting all the colors of the rainbow. So you can do the same with hydrogen. But hydrogen isn't going to give out any light without some encouragement. So you need to excite the hydrogen by forcing a high voltage through it. And this causes it to glow pink. Now this pink light, so this light is split just like we did with the white light. So it's coming into the prism and getting split. But what we are not getting a continuous spectra, or even part of it. So we're not even getting the bits that contain the pink light. What we are getting is an emission spectra. And then also, just to let you know, this is only part of the spectra. So the bit that we can see, so the visible lines, there are also lines at higher energy. So at higher energy would be over here, and this is UV. And then there's also some lines at a lower energy, and this is part of the infrared part of the electromagnetic spectrum. So now let's link this spectrum. So what we can see here, these observations, let's link this to atomic structure. So so the key thing is, because we are getting these fixed lines and these fixed lines only, electrons must live at shells that have a fixed energy, and that there is a fixed energy between the shells. So let's go over here now. So the first thing is that the light we are seeing here is visible. So these are all visible lines. So we've got our colors that we're hopefully familiar with. And then the rule with this is, if you can see the visible line, then the electron has gone from a higher energy, and it has to end up in n equals 2. So this is just something that you need to remember, and we're going to look at this in more detail in a minute. So the next thing we need to figure out is why the lines are not equally spaced. So we can see that they are starting to get closer together over here. We've got a really big gap here. So the fancy way of saying that the lines are getting closer together is we can say that they are converging. So they're converging over here. In fact, they're converging at a higher energy. So the observation is that the coloured lines are getting closer together. So now we need to link this observation to atomic structure. So we have n equals 2, so this is the second shell. And then we've got 4 energy levels above n equals 2 in our diagram. So when an electron goes from a higher energy shell to a lower energy shell, a photon is emitted. So when an electron starts here and ends up over here, a photon is emitted. So from the diagram, we can see that all of these distances are different. So this is the biggest distance, and this is the shortest distance. So the bigger the gap, so this is the biggest gap, so the bigger the gap, the higher in energy the photon that is emitted has. So purple light has the highest energy, and that's matching up to this line here. And that's coming from the photon going from N6 down to N2. And we've got N5 down to N2, so that's that line here. Then N4 down to N2 is this line here. And then we've got a huge gap, a huge difference here. And this is N3 down to N2, giving us this line here. So for the higher energy photons, the gap in energy between them is smaller. So we can see, because these lines here are closer together, you can see that the length of these lines is similar. So this is because as the shell number increases, the gap in energy between the shells is decreasing. So the lines are converging because the shells are getting closer in energy. So these shells, so these 3 shells here, are much closer in energy if we compare them to these shells. So these are the furthest apart shells. So the final thing is, what part of the electromagnetic spectrum does the emitted photon belong to? So onto this diagram. So if you're ending up in n equals 1, so if the photon ends up back there, you are getting UV light, because this is the biggest gap, and the bigger the gap, therefore it has the most energy. So we can see all of these photons heading back to N1. That's a really big line, so that's a really big gap, so that must have the biggest energy. So you're back to N2, so this is what we've kind of already been talking about. So so this gives us visible light. So these 3 going back to N2 is giving us visible light. And then finally going back to N3 is giving us infrared light. So infrared has the lowest energy, and then this has the shortest line. So they do have fancy names, but you don't need to know what they are. So in summary, we are observing fixed wavelengths, specific colors of light. So we're observing these fixed wavelengths with their specific colors. Each color has come from a photon emitted from a hydrogen atom. And as it is an emission spectra and not a continuous spectra, the energy levels within an atom has to be fixed. And the colors are getting closer together at higher energies. So the colors are getting closer together at higher energies. And this is because the shells within an atom are getting closer together at higher levels, at the higher energy levels as well. So now moving on to number of electrons in each main energy level. So here is the table that we have got loads of information in. So we have principal quantum number. So these are just the shells, so N1, 2, 3, 4. You can go all the way up to 7, so N goes all the way up to 7. And then this is the really important formula here. And this is telling us how much, or this is what you use, to calculate the number of electrons. So we can go through a little practice calculation. So it's nice and easy for 1. So you do 2 times 1 squared, which equals 2. So that is, 2. So that's where this 2 is coming from. If we do for our next one, so 2 times 2 squared is going to give us 8. So so the second shell can hold up to 8 electrons. So this is something we're hopefully familiar with. And then this is where this is like all the new stuff over here is when we start to look at the orbitals. And then we can carry on going through and doing all of these calculations if we want. But so this tells us the total number of electrons that you can get in each main energy level. So if we just have a look at our atom, so if we just get our nucleus, we've got our 2 shells, so we know that 2 electrons can go in the first shell. In the second shell, we are getting 8 electrons. So yeah, so this is all stuff that you should know before IB. What we're going to look at now is, in a little bit more detail, is a bit more specifically where these electrons live. So with n equals 2, we've got our 8 electrons, but yeah, they are broken up into sub-levels. So 2 of these electrons can live in an s orbital, and 6 of them are living in a p orbital. So this is what we're going to move on to now. Well, I say now, but I mean in the next video. We all need a little break every now and again, don't we? So if you are enjoying the electronic configuration content, definitely watch the next video. And if you want more IB chemistry videos, then it would mean so much to me if you liked and subscribed. Also, if you want more help with chemistry and are aiming for a 6 or a 7, then tutoring is a great way to get there. And if you want some tutoring from me, a fully qualified teacher who has been in the business for over 10 years now, check out my website, link in the description. Right, so catch you in the next one, where we'll be finishing up with SL electronic configurations.